Good morning everyone. So in today's class we are going to talk about vertex cover and matching number. Recall that in the last class we were discussing independence number and dominance number. So to begin with, vertex cover is a set of vertices such that every edge has an endpoint in S. Do not get confused with vertex cover and dominating set. We will see the example. So if you see this example, then you can see that it is a vertex cover of size 5, because all 5 vertices, if you take in the vertex cover, then all the edges of the graph either have one endpoint or both the endpoints as these vertices. So this is why it is a vertex cover. These are one few more examples. So again you can see that here these three vertices, if you choose, then all the edges are incidenting to these three vertices, and again in the other graph the same can be seen. So vertex covering number, which is denoted as beta g, is the minimum cardinality of a vertex cover, which means we are looking for a vertex cover of the smallest size. So these are the vertex cover. Do you think that these vertex cover are minimum? Please do try by yourself. So you can observe that both of them are not minimum, because in this case you can choose these two vertices and all the edges would be covered, because this edge is this vertex is actually covering so many edges. And similarly in the other case, if you choose 3 vertices instead of 4, then also our job is done. So vertex cover, or the beta g for this graph, is equal to 2, while for this graph it is equal to 3. Compute the vertex covering number for Peterson graph. Take it as exercise. Please do try by yourself. So for the Peterson graph, it comes out to be 6. Moving further, what is the relation between vertex cover and matching of a graph? Instead of matching, we can talk of the matching number, which means the cardinality of maximum sized matching. So if you recall from the last section that we have already discussed how to find the matching number. Also please do remember that the dominating or dominance number for the Peterson graph was 3, while for the Peterson graph the vertex covering number is 6. Okay, so to find a relation, better again to think about the Peterson graph. So with vertex cover, the vertex covering number for the Peterson graph is 6. Now what is the matching number of a Peterson graph? Please do try by yourself quickly. So you will observe that for the Peterson graph the matching number is 5. So matching number is 5, which means Peterson graph we know that the order is 10. So size of the maximum matching would of course be 10, of course be 5, and we found a matching of size 5, which is the maximum matching. So from this example, one observation is that matching number is less than equal to vertex covering number. But is it true always? Or you can see the question like this, that does there exist a graph where the matching number is greater than the vertex covering number? Or if not, then why it is not possible? So interesting observation here is that when you are looking for the matching number, then in the matching number all edges are independent. Yes, and each edge has 2 endpoints and there are no endpoints in common. It means that to find a vertex cover we need at least these 5 vertices, not exactly same, but at least 5 vertices, otherwise these 5 edges would not be covered. So any 5 vertex are required. So you can see here also the 5 vertices are there, 1 2 3 4 5. So surely these 5 vertices are must, because edges are independent. Without these 5 vertices you cannot cover these 5 edges, and there can also be the other edges which are not covered. It means it is at least 5, or the vertex cover size should be for sure greater than equal to 5, and that's why you can say that the matching number is always less than equal to vertex cover. So very interesting example, very interesting result, which says that alpha dash g is always less than equal to beta g. So you can quickly read it down by yourself. M is the maximum matching, S is a vertex, minimum vertex cover. For every edge in M, there is an end point of this edge E in S for sure, and this is why alpha dash g is always less than equal to beta g. From there we can also conclude that if the size of the maximum matching is equal to the size of the minimum vertex cover, or size of the vertex cover, then M must be maximum matching and S must be a minimum vertex cover. Yes. The more interesting question is that, does there exist such graph where alpha dash g is equal to beta g? Can you think of such graphs? So please think and then look for the answer. I am giving you one example. So if you see this example, then you can see that the maximum matching is 4 and the vertex cover or the minimum vertex cover is also 4. Please verify by yourself. Now can you categorize these graphs? So if you see this graph, then it has no odd cycle. So even you can observe that for all the bipartite graphs, even for the trees, for the path graph, or any graph with no odd cycle, alpha dash g is equal to beta g, which means that we can say that if g is bipartite graph, then alpha dash g is equal to beta g. So these are the invariants which we have discussed so far. Maximum independent set, which is alpha g, maximum matching, which is alpha dash g, vertex cover, which is beta g, and edge cover we will discuss. The important observation is that these two invariants are related to vertex set, while these two invariants are related to the edge set. One more interesting question is that, what is the relation between alpha g and beta g? So alpha g is the independence number, beta g is the vertex covering number. To conclude, again recall the Peterson graph, and for Peterson graph we already found that beta g is equal to 6. Can you try to compute alpha g for Peterson graph? So if you try to compute it, you will observe that it comes out to be 4. So for the Peterson graph, the important observation is that the union of vertex cover and independent set is giving you the vertex set, which means that here alpha plus beta is equal to n. But how do we prove it? To prove alpha plus beta is equal to n does not look obvious. But if I write this statement in this way, that S is an independent set if and only if S complement is a vertex cover, then of course their union always gives you the vertex set. Now how do we prove S is an independent set if and only if S complement is a vertex cover? We will start from one side. So let S is an independent set. Now S is an independent set, then recall any edge, let's say edge E, if its endpoint are U, V. So both U and V cannot belong to S. So U and V cannot belong to S. One of them can belong, but not both. It means that for all the edges, one of the endpoints should always be in S complement. and which clearly indicates that S complement becomes a vertex cover because it has endpoint of all the edges, either one endpoint or both the endpoint, but for sure it forms a vertex cover. Other way around, if S complement is a vertex cover, it means that it has at least one endpoint of each of the edge. It means both the endpoints cannot belong to set S, which means that S is an independent set. So very interesting result. You can read it proof again by yourself for a better understanding. So the last topic which we are going to cover is edge independence number. So we have discussed mainly 4 invariants. Can you relate any of the invariant with edge independence number? So you can observe that edge independence number, which means we are looking for the maximum sized set or independent set of edges, which is actually we are looking for the matching number. So matching number can also be called as edge independence number, which is denoted as beta 1g. Quickly try to compute the edge independence number for cycle graph, complete graph and complete bipartite graph. So if you see the cycle graph C4, then maximum 2 edges can be independent, and for C5 also maximum 2 can be independent. Even if you think of K4 or K5, then also maximum 2 can be independent. If you think of K23, then again only 2 edges can be independent, and from there we can generalize that for Cn and Kn, edge independence number is n by 2 if n is even, and it's n by 2 minus 1 if n is odd. And for complete bipartite graph, it is minimum of m comma n. So the last invariant which remains is the edge covering number, which we are going to discuss in the next class. Thank you very much.